Now since we are assuming that the wear rate is constant, while so this product is equal to constant, but the pressure is not constant throughout the surface. So it means that the pressure is going to vary from inner surface to the outer surface. And in fact, the maximum pressure will occur at the innermost surface of the clutch, while as we move away from the inner surface, the pressure will decrease. So the same expression we can actually write as P maximum, which will occur at the inner surface, and it can be equated to K. Now if we solve these two equations, since the right hand side of these two equations is equal, so we can actually compare the left hand side, and what we get in the end is that P is equal to P maximum Ri divided by R. So this is the expression that we can get by solving these two equations simultaneously. Now next, we can write the same expression for the actuation force F as we did for the previous derivation. So it will be an integral of 2 pi r P and dr from the inner radius to the outer radius. Except that in this case P is not constant, as was the case last time. This time this P expression will be substituted from here. So we can write integral 2 pi r, and then we can have this expression of P max R I over R, and in the end we have dr. So this R and R cancel out, and what we get as an expression of F is 2 pi Ri, which is the inner radius. Then we have this P maximum, and inside we have R naught minus Ri when we expand this integral. So we will get this R naught minus Ri. Similarly, we can write an expression for the torque. Now for the torque, all we have to do is we have to multiply this force with the radius. Right? So when we multiply this expression of force with the radius, so this is what we get: Ri R naught 2 pi R P dr, and this is the R that we are multiplying with. And again remember, just like last time, we have to multiply by mu, because torque is equal to the frictional force multiplied by the radius. So this was normal force. This F expression was normal force. So we have to multiply by mu to get the frictional force, and then we multiply by the R. So what we will get is, we will get pi mu Ri P max R naught square minus R I square. And when we again replace this P max here by using this equation, what we will get is, we will get a simplified expression for T, which will be N mu F R naught plus Ri divided by 2. So here N again is the number of the clutch surfaces which we have introduced in this equation, and this is the expression for the actuation force. So these two expressions are applicable for the case of uniform wear condition. Now this model, this uniform wear model, I'm going to rub this part. There are a few points to note here. This uniform wear condition model, it gives a more conservative clutch rating, right? So it means that if we use this model and calculate the number of clutch surfaces or the size of the clutch, this set of formulas will give us a larger value of the size of the clutch. So it is more conservative. We call it more conservative, means it will give us a larger value. And it is actually a preferred design by the designers. Preferred model. Similarly, you might have noticed this expression of P max, which appears here. So this P max is actually seen from the table. So this is the maximum pressure that can exist between the surfaces, and this we will see from a table in the book, and it depends upon the lining material. The clutch surface is lined with a certain material so that it does not slip. So different materials have different coefficient of friction and they have different P max values. So this will be seen from a table depending upon the lining material. Lastly, we obtain maximum torque transmission when the ratio of the inner to outer radius is 0.577. So when Ri over R naught is actually 0.577. So this is the ratio, this is the golden ratio that we will be using. So every time if we are given with the inner radius, we can calculate the outer radius by using this expression. So that is all for both of these derivations. Now we will move on to solving the numerical problems related to this design.